So what I want to discuss today is this question that, let's go back for a second to classical mechanics and just write, if you have a bunch of point particles, right, they are described by Newton's law, something like this, that the acceleration, mass times acceleration is equal minus the gradient, right, of some potential that it may depends on the position there is, say, a generic potential. I don't really, that depends on the relative distances of this bunch of particles. And if you remember, these equations are invariant in form under translation, rotation, and transfer. So they are invariant under translation, right? So if you translate your axis, so from y to y prime, say, and then the z comes out from this way. Okay, these two are two equivalent sets of Cartesian axes. So if you do this transformation, you know that these equations are invariant in form. That is, you can put the prime everywhere, right? And it's still okay. They maintain the same form. Okay, and in fact, it's even more than that because you can also rotate your axis, right? From y to y prime and from x to x prime. So you do a generic rotation. Now I don't want to, I mean, you do a generic rotation and clearly the Newton's equation remains the same in form. I mean, it has exactly the same form in the prime coordinates than in the unprime coordinates. Okay, that's sort of, in fact, you remember that these transformations, they are linked with the conservation properties of your system, right, in general, that if you rotate, if there is rotational invariance, then you can deduce and so on. But the most important transformation is that if you go from a frame, right, that you have so you do a transformation from one set, say, y and to y prime, and now these two sets, let's assume that it moves by keeping the x direction unchanged. By a transformation, you go to a new system that is moving with constant speed v with respect to your original set of coordinates, right? That means x prime is equal what? X minus vt. And then because I mean, it could be, v could be a vector pointing in any direction, but let's assume that points in this direction. Therefore, you see that y remains y, z remains z, and in particular t remains t. Okay. This kind of boost, I mean, this transformation from moving is called, I mean, the invariance of Newton's law under this set is called Galilean. How do you write Galilean invariance? I mean that they are all inertial. You see, system frames of reference moving with constant speed, they are inertial, right? You remember from before Christmas. And the physics is the same. What does it mean the physics is the same? It means that Newton's, you can write a Newton equation and it remains exactly in the same form. You just put primes there and there, and it's exactly the same. You can check that this is so for this transformation. You see, you could check for translation. I mean, clearly the translation invariance is due to the fact that this potential only depends on the relative distances, right? I mean, and rotation is the same. And in particular, this is true because you see that the velocity remains the same under this transformation. the gradient remains the same, right? It's not affected, and this relative distance remains the same, because if you have a relative distance like this, then if you move with respect, you measure that, it remains just the same. Therefore, the equation, indeed, they remain the same if you put the prime, okay? And you can check, in fact, it could be just an exercise that you can check that if you rotate you do a rotation of your coordinates, again, this remains the same. But this, in a way, the fact that it remains the same is due to the fact that you can write this as vectors, and so it's invariant under rotation and this kind of translations. Okay. Now, this is a very profound statement. I mean, I hope you appreciated last year when we first discussed it, and because it's not so obvious, right? If you ask the first guy, it will not be so obvious, right? And it comes from the fact that the force depends only on the acceleration, right? So because it depends on the acceleration, then if you're moving with constant speed with respect to this room, then the laws of physics are going to be the same, right? And we also study examples in which this was not true, that was non-inertial frames, right? If you are rotating or you are accelerating, then you will see that the laws is changed. You have extra terms, right? Extra terms that are not here, like Coriolis force and so on and so forth. Now, this was very clear to Galileo, and in fact, that was his main contribution to physics. And he essentially observed, right, that if you are on a beach and you look at people on a big ship moving across, right, and they toss a ball or they exchange something, they run, everything is exactly as if they were on the beach, right? Even though their frame of reference is the one moving with the big ship, right? Now we talk about spaceship, but the idea is exactly the same. Now, so why I'm discussing this? Because this is a sort of the principle of relativity for Galilean physics, right? The principle of relativity says that the physics is the same no matter what frame of references you are picking, as long as they move with constant speed with respect to each other, so they are not accelerating. In fact, when the people talk about relativity, it's just the opposite, right? Because one thinks of relativity that something depends on, right? But it's exactly is the principle of invariance rather than relativity, because you understand, it's just telling you that for all those frames of reference moving with constant speed, the physics is the same, is invariant. Okay, so this term relativity is really not a very good term for this stuff. Anyway, now, however, we know more than this, right? Because we study electromagnetism, and a natural question is, now, for instance, we have Maxwell equations, or even simpler, we have the wave equation, the wave equation that we study, right? That is this gradient of this gradient square, right? Minus 1 over c square d square dt square of some function depending on x and t equal to 0, right? Here it could be the electric field, the potential. We discovered that in empty space, Maxwell equations give rise they give rise to the wave equation, okay? And so is this equation invariant under these Galilean transformations? So that's a natural question that one may ask, and the fact is that they are not, because you see it comes from the fact. So we have this. Essentially the critical one is this with the velocity, right? That you have x prime equal to x minus vt, and you see that it has to do with the say the x derivative of psi. Say this is okay, right? It's not going to, and the same for y and z. okay? But you see that the time derivative, it may lead to trouble, because the time derivative of this, right, you see that it's like minus v d psi dx prime plus d psi dt prime, right? So this is not equal to this. It has an extra term because of this dependence in the transformation, right? So you go from the prime quantity to the unprime quantity, not in the simple form that would lead to an invariance, okay, but to this sort of mixed term. And you see when you go to the second derivative, you have to apply this twice, right? So you see that the second derivative of psi with respect to the time, that is this term here, well, he gets an extra term. I mean, this would be the invariant term, right? But because of this mixed term, he gets one term that comes from the mixed derivative, right, when you take the time derivative of this, and then he gets the extra d2 psi dt prime square, right? So even though this is invariant, this is not. So if you do so if you transform your wave equation from a system at rest to one that is moving with respect to that with velocity v, you get extra terms. So this one, it's okay, it's the same. But then you get extra terms coming from those. So you get the 2c square, the one with the v, right? So v now is a vector. This I did in one dimension. So it's a v vector, the gradient of the ddt. And then you get the v dot delta square, right? Acting on psi. So you see the equation is not invariant in form, because even if when you put the prime right here, you get all these extra terms. But this is okay, I mean, because that is correct for a wave equation, because you know that the wave equation describes the motion of waves in some medium, right? And if you are moving in this medium, so like myself, now I'm talking and I'm moving, and the medium is the air of this room. And you see what happened is that the property of the sound waves depends on the medium, not on the fact that I'm moving, okay? So they are not invariant, I mean. The fact that I'm moving now is changing this situation, and therefore is that what you expect is in fact that the wave equation is not invariant. Is that clear? I mean, because the velocity of sound does not depend on the fact that I'm moving. It depends on the property of the medium, right? Therefore, it's not the same, okay? They are all the same, even if I'm moving. Why you'd expect that if you were moving, they would sum up, right? That the velocity of sound will become higher if I move toward you, and lower if I move away. And even not symmetric the situation, because on the contrary, if you are moving, that the frequency of the wave changes, because that's the Doppler effect that you know now, right? Okay. So you see that the wave equation, by its nature, is not invariant under the Galilean transformation. So here we have a problem, right? Because we have half of what we learn, that is all this Lagrangian classical mechanics stuff, is based on this invariance. And now half of what we learn, that is the Maxwell equations and the wave equation that follows from that, that satisfy another set of invariances. Okay? So what are you supposed to do? They don't work together, right? By the way, you can think, what about Schrödinger equation? Is that invariant under Galilean transformations or not? Well, actually, it's more subtle than that, because there you have more freedom, because you can multiply the wave function by some phase, right? And it's not going to change much. So you may think about that, take it as a homework, but we are not going to that the Schrödinger equation actually it is invariant under this. But of course you get the psi that gets shifted by some phase. Okay, but that's okay because it's a phase, so you know. So that has to do it's not the wave equation, strictly speaking, the Schrödinger equation, because it has the first derivative here, right? In fact, one of the problems of the Schrödinger equation that is not invariant on the transformations that we are going to discover that the wave equation is, right? So strictly speaking, I mean, the Schrödinger equation is not invariant under Lorentz transformation, of course. But it is invariant under the Galilean transformation, so it's fine. The Schrödinger equation is okay. The wave equation is not. And I guess people knew about that. And they study Lorentz and others. They study, so they ask themselves, what is the set of transformations that leave this equation invariant? Okay, and probably you already know the answer, but it's easy to derive what are the properties, because you see, for this equation to be invariant, that means that the wave, say a spherical wave, a front wave, right, satisfy the fact that s squared plus y squared plus z squared, right, minus c squared t squared is equal is the same in all frame of references, so it's constant. So that means right, this is the wave front is invariant under this transformation. If this is so, then the wave equations are invariant. So what is the transformation that leaves this invariant? That's easy to compute, but first it's useful to call, you see, the front wave of a wave, it has this character, because that moves with velocity c, it has this characteristic signature, right? It has the spatial parts minus the time parts. So except for this c, the t behaves like a coordinates, right? And so you may as well call this c times t your first coordinates, so that then this looks like simply what? Just if you call x naught this, then x1, x2, and x3, right? Your four coordinates, okay? Then this becomes very simply that the length of this vector, but it's a peculiar vector because of this minus here, is constant, right? That means that x mu, this is x mu, the components of x mu. So x mu square, right, where you sum mu from 0 to 3, where 0 is the time component of this vector, remains the same, right? So that's the requirements that you impose. And then, so what is, this is a linear transformation of coordinates, right? So x prime mu is some sum over, say, nu, a mu. So these are a matrix of coefficients transforming these vector components, right? That's the generic linear transformation of a vector with components x naught, 1, 2, and 3, right? And you see that in order to have this to be true, to preserve this, or this better, this to be true, well, of course, this is a transformation in which it's an orthogonal transformation, so you can add the property that a mu nu, right? So you raise a index and then you multiply, say, by another one. Nu lambda must be what? The Kronecker symbol, right? That's the definition of an orthogonal transformation, okay? So these are linear orthogonal transformation sending you from this from these coordinates to these new coordinates, and you want this a mu nu, okay, these are the transformation, to be such that the length of this vector remains the same. It's invariant because the length of the vector of the position defined with this odd sign here, if that remains invariant, then you have the invariance of the front way. Okay? And you see that, let's do it for, so this is in general, but let's do it for a particular direction. So let's look at the transformation in the x1 direction, okay, beside time. So that matrix A, you see, if I'm looking just at the 0, 1 components, it is made like this, right? 0, 0, 0, 1, 1, 0, 1, 1, and then the rest is 0, 0, 0, 0, 1, 1, obviously. 0, 0, 0. Is that enough zeros? Yeah. No, some 0, 0, right? Now, you see that if you impose that the length to satisfy this, you get that, what? A0, 0 square minus A0, 1 square must be equal to 1, minus I1, 0 square plus 1, 1, 1 square must be equal to 1, and then the product, like A0, 0, A0, 1 plus 1, 0, 1, 1 must be equal to 0, okay? This because of the... Now, so these are conditions on the coefficient. So I'm looking at the same case I was looking before, just something moving in the x direction, okay? And then nothing is going on in the y and z direction. This is this condition on the orthogonality of this coefficient. Now I'm doing the transformation. So you see that x, so let's start from x prime 1 equal to 0, right? So you see that the transformation, I'm doing this Galilean, the transformation to the motion. So x1 must be equal to vt, right? Or if you reintroduce the x1, this is t, so this is v over c x naught, right? This v over c keeps on popping out, so I give it a name, beta, and so x naught. So here I'm just rewriting t in terms of x naught. So you see x1 must be beta x naught, right? So what is x1 prime? x1 prime, I read it off from here. x1 prime is a11 x1 plus a10 x naught. So then by using this thing here, you see this is x naught a10 plus beta a11. But you see, I started out with x prime in equal to 0, so that means this must be equal to 0. Okay? So a1 naught must be equal minus beta a11. On the other hand, also this is true, that you see, minus a1 naught square plus a11 square. So from this and that, you see that you get that a11. So I use this to rewrite a1 naught in terms of a11. So then I pull them out. So I see that a11 square, 1 minus beta square, must be equal to 1. So from here, I deduce the value of a11. a11 must be 1 over 1 minus beta square. square root. But then, if I know A11, I know A10 because of this. It's just minus beta 1 minus beta square. Okay? And from here, I get the other. So you see, by imposing this condition, I deduce the value of the coefficient A of this particular transformation that leaves the front, the shape of the wave unchanged, right? Because I can write this matrix in this case to be equal to 1 over square root of 1 minus beta square minus beta 1 minus beta square, then 0, 0, and then A10 is just minus beta 1 minus beta square, 1 over 1 minus beta square. Then I have 1, 1, and then zeros. In fact, this factor here gets the name gamma usually in the textbooks because, so you have gamma and beta. Beta is the ratio of the velocity of the transformation with respect to the velocity of light, and gamma is this, this combination of these factors. Okay. So now you see you can write individual components because now this is the generic transformation that leaves this expression invariant. And I can write, for instance, what is x prime meaning x1 in terms of this transformation, because you read it off from the transformation matrix. It's just this factor gamma that is here everywhere, right? And then you see is x minus vt. And what is t prime? You see t prime is not t. It cannot be t because of the form of this transformation. You see t prime 2 gets transformed, and it's this factor gamma t plus vc square x. For this particular choice, then you have that y prime is equal to y, z prime is equal to z, because you are transforming only in that direction. Okay? This in general is called a boost, because it is a boost. It's a boost to go to a new frame of reference that is moving with velocity v, or beta in units of c. And you see the particular fact is that this looks like the Galilean transformation, except for this boost factor gamma that somehow popped in because of this requirement of leaving this wave unchanged. But okay, that you could live with that, even though, of course, it's a very important factor, because you see that as your speed comes close to the speed of light, this beta comes close to 1, and you hit a singularity. But this is more sort of worrisome, because t that you were used to, t prime equal to t, after all t is t, is not any longer the same. You get not only the boost factor gamma, but you get a shift in t coming from the position in space. So that is already telling you that the transformation leaving the wave unchanged are going to change your idea of simultaneity. Because before, t prime was equal to t, so now here was exactly the same now for the observer moving with some velocity v with respect to me. We all agree with our clocks. But now this is not longer true. Our clocks are moving at different time, with different speeds, so we have to worry how to synchronize events in these things, right? Huh? No, I think it should be a plus. No. I think I have plus. Oh, do you see minus? Let's see. Boost. Yes. No, you're right. T gamma T minus. Okay. Thank you. Now you can convince yourself that these transformations are correct for the case of the wave. In fact, for this very simple case in which we are boosting in the x direction, that is, the velocity is all in that direction, these are left unchanged. So let's assume that they are at the origin and they remain at the origin. So this part is just 0. Then you see that the wave condition is simply that if x is equal to ct and x prime is equal to ct prime, right? So you can apply your transformation and verify that, in fact, this is the case, that if you boost, they remain invariant. This is not the case with the Galilean transformation. If you have t fixed and x prime changing, obviously, this cannot be satisfied. But we already knew that, right? Now, these transformations, of course, you have the corresponding one. So this is a boost in one direction, but in general, the v is a vector, so with components along x, y, and z. So you have components also in the other elements, okay? But it's easier to just think of a single boost. And of course, this is a Lorentz transformation. That they are the transformation that leaving, as I show here, are the general transformation leaving the front wave, the shape of the wave unchanged as you change from a frame moving with respect to the other with velocity v. Of course, there are several. You already knew that. I take it. You knew that these are the Lorentz transformations, and probably it was stressed to you that because of this fact of mixing x and t in the transformation, not leaving t separately, they introduced this idea of space-time that we are going to, that is, you cannot talk any longer about a point in space, you have to talk about a point in space-time, because you see every time what is in a position in space at a given time for one observer is that thing in a different position in space and time for another observer, right? So this is very, very different of what we had before, because if I'm moving, say you are on the usual train, right, and you move by in the Newtonian or Galilean system, you agree on the time, as I said, right? You say it's 3 o'clock and you are here. If you are moving, you are there, okay? That was the idea. But now that's no longer true. I mean, you also have to agree on the time. Before we discuss that a little more, let me point out that this Lorentz transformation, they form a group, just mathematically speaking. And so I'm not sure I want to discuss that much. But so they form a group. Usually maybe L is called or some other. And it's a group, as I said, that leaves this distance unchanged, right? And you see that you can write this distance by introducing what. So let me erase this. So I don't know how much you want to know about this, the group structure of the Lorentz group, but you see this is a distance, right? So distance is, so it's like, as I said, so x1 plus x2 square plus x3 square minus c square t square, right? This is, I call it x naught. Usually a distance is defined by a metric tensor, right, in space. This is a flat space-time. And because you see, you can write this as you take the transpose of this vector, you multiply by this matrix, let's call it G, and X, and you get this, right? If G, you see, it has, so the zero, say if you call this the zero component, then you see the zero component gets a minus, and the others are just 1, 1, 1, and here 0. Is this clear or? No, it's completely, so I take it, so the position is made of x0, x1, x2, and x3, right? This is time, x, y, and z. So I take the transpose, so this is x0, x1, x2, and x3. Then I have a matrix, and then I multiply x1, x1, x0, x1, x2, and x3, right? This is what you do when you multiply two vectors. Usually, you didn't write this part here, right, because it was trivial. Before, it was just 1, 1, 1, right? Forget about the not. In space, we didn't write this part here because it was just the identity matrix, so who cares, right? So you just multiply this by this, and you got the length of this vector. Now, however, it's almost like this, but you have to be careful because when you multiply x0, you get a minus. So you have to remember that you have a minus. So it's a good idea to write this product, put in the matrix here. Okay, this matrix is called the metric. It tells you the signature of space-time. Is that any better or now? Or do you understand it now? Yeah. So space-time is characterized by this. All spaces are characterized by this metric matrix, a tensor. But in particular, this is a flat space-time. Don't worry about the term, but because you see it's diagonal. But it has this important property of having a minus here. That's the reason why time is not, I mean, it's there in space-time, but it's not like space, right? Time is a very particular coordinate. Okay? So this thing that I did, one piece at the time, that is the invariance of this under the transformation, and then we discover that your coordinates must transform like Lorentz said, is imposed on the invariance here, right? Okay, and you see that the Lorentz group, that is the set of all the transformation. If you so a generic transformation, you could call it lambda, right? And then you see that the invariance of this becomes the invariance of, in this form here, the metric tensor is invariant, right? This is the property. And you see that this generic transformation, in fact, has a property that the determinant of this Lorentz transformation must be equal to 1. Okay? These are called the proper Lorentz transformations. You also have the non-proper Lorentz transformations, you understand, but the proper Lorentz transformations are the ones that can be reduced to the identity, right? The non-proper, the one with the -1 here, are those that include the inversion. Here you don't have the inversion, right? The x going to -x. There are two sort of subgroups. So the one that includes the identities, that is the one we want to stick to, is called, so if this was the Lorentz group, this was the proper Lorentz group, maybe L plus. And if you also require that the 0, 0 component, remember that matrix I wrote there, is greater than 0, okay, these are the orthochronological Lorentz transformations, sometimes indicated in this form. And how many are the parameters of this Lorentz group elements? You see, it's a 4x4 matrix, right, the transformation. Remember the one I wrote here, A00, A11. So in principle, there are 16, right? But you have many conditions, you see, that they have to satisfy because they are orthogonal and orthochronological. And so you get 10 conditions, okay, if you count. So 16 minus 10, it's 6. So you get 6 parameters characterizing this transformation. So this group is made of, and what are these 6 parameters? Well, 3 you must tell me immediately, because these are the rotations, right? So what are these 3 parameters? The Euler-Langos. You see, they came back. And the other 3 are the boosts. So the Lorentz transformations are made of rotations, okay, And then the boosts, that are these transformations where you boost from one frame moving at a certain speed to another one moving to another speed. And you have 3 of them, because here I just wrote one that was the boost in one direction, but you can boost in any directions you want, so you have 3 boosts. So 3 Euler angles and 3 boosts are the 6 parameters of the Lorentz group. Where are the translations, you may wonder? Well, they are not here, because here I'm assuming, you see, that I keep I'm not including the translations. Those are members of a larger group that is called the Poincaré groups, where you also put the
You said we have a condition of orthogonal and also
this condition or the
no, just you said
they are orthogonal transformation, like rotations, with determinant equal to 1, right? This is like the group of rotation, O3. Then you impose this condition, and you get SU.
no,
Is that the question? No.
no. You said you have to also one is orthogonal condition, then also canonical.
What are the 10 conditions? That's okay. I leave it as a. Yeah, I wrote them here, and I leave it as an exercise. But you understand, some are these orthogonality conditions, then these conditions, and this. So, I mean, it's no big deal. So, this about the Lorentz transformations, and you see that we are forced upon us this concept of space-time, right? So we have to say something about space-time, I guess. Usually this idea of space-time is not, I mean, everybody knows about space-time, but then when you start discussing, you realize that the weirdest ideas are, for instance, what is your idea of a time machine? Well, I know that you cannot build it, but you know there are many books. The very famous Wells book, The Time Machines. The idea generally is that you have a machine that you turn it on and it transfers you somewhere else in time, right? And you understand that this is a completely wrong idea, right? Because let's say that we have this machine here now, right? You want to go back, I don't know, to 200 years ago, right? So, and the machine does that exactly. It just moves you from time now to time now minus 200. You see, that's a very dangerous machine, even if you build it, because you push the button and you die, right? You understand why? Why? No, that's not, I don't, it's more simple. Let's assume that you have bypass all this paradox that you kill your mothers and all stuff. That's a minor point. You get killed because 200 years from now, the Earth is not here. It's very far away. So you come up in empty space and you die. That's the reason why nobody came back from the past, if that is a time machine. You see, the time machine is really a space-time machine. If you ever want to build one, you should build a space-time machine, something that moves in time and space, you see, because they are always related. Like if you want to go back here in Trieste 200 years ago, you have to move 200 years in time, but at the same time you have to move in space where the Earth and our galaxy was 200 years ago. And it's very far away because, as we said, the Earth moved 50 kilometers per second, and then the galaxy is moving toward Vega with even faster, so you see. So they always come together. So they must be discussed together. But to discuss them together, you need to define. So let's say this blackboard is space-time, right? And we are used that the distance, right, on this blackboard, right, x and y, the distance is defined by this quantity, right? That's the other thing. But you see, the problem with space-time, as we said, is that it looks like, almost like this blackboard, except for the sign minus, right? So the distance in space-time is not this. If this blackboard, it has x here and time there, the distance there is this. It has this sign. And this is very important, because if you start measuring distances in this, so let's assume this blackboard has a metric, as they said, with this minus here. This is called the Minkowski metric, by the way. Okay, so let's assume this blackboard is the Minkowski, has a Minkowski metric in one spatial dimension and time, of course. Then you want to, so here you have Ct, or x naught, as we introduce it, and here you have x. And you have all these lines. You know, this is the measure of this distance. And then you have points, say A and B. And so no, A, I call it B here, B and C. Okay? And also, you also have, so I keep on, well, that's really bad, but I also want to have, say, A prime, then I go up here to C prime, and I have B prime here. Okay? Something like that. Now, if you start measuring, you see it's a bit funny, because, so 1, 2, 3, 4, well, I wanted 5, so AB, the distance AB, you see is 5 squares, right? And AC, okay, so BC is 3. Okay. Now, how long is AC? Well, you use the Pythagoras theorem, but you must be careful, because you have this minus sign, right, in this direction. So AC is 5 square, right? But when you go this direction, it's not plus, it's minus. So it's minus 3 square. So AC is equal to 4. So this is 4, this is 5, and this is 3. So you see, it's a space that has some weird property, because AC is less than AB. And here is even stranger, because, let me put it like this. Say A prime, B prime. Let's say this is 3 squares. It's a little less, but as before, say it's about 3. And also this should be 3, right? Because I draw it symmetrically. So also B prime and C prime is equal to 3. But now, how long is AC? You see, yeah? No, I'm sorry, I made it wrong. So this is, I computed this 3, right? So let me draw it correctly. A, B. I draw it, so I want 3 square here, or let's say 2. Let's say 2. You see, how long is A, B prime? Is 2, right? 2. And then 2 here, but it's 2 minus 2. Okay, so I made it wrong. So it's the square of 2 square minus 2 square, so this is 0. So the distance from here to here is 0, and the distance from here to here is 0. And the distance from here to here is what? Well, you count 1, 2, 3, 4. So you see, it's a very weird thing, because as you move in this direction, it counts for, is 0, this distance. And this other one is there. So you have to get used to this structure. And the best way is usually to draw a space-time diagram. Did you understand this? Because I messed it up a little bit. You did not understand it? Well, just count, you see, you start counting the square. So the distance from here to here is 1, 2, 3, 4, 5. Right? the distance here is 3. Then you compute the third distance by using the Pythagoras theorem, but remember that you have to put a minus because of the metric. So then you get 5 square minus 3 square is whatever it is. Here you do the same. Now you want to measure this, so you take this 2 square plus this 2 square, but this plus 2 square has minus 2 square because they are in the t direction. So this is 0. In this metric, in this space, this distance, even though it looks different from 0, is effectively 0 because of the metric. This is all the secret that you have to learn about the Minkowski space-time. So let's draw these famous space-time diagrams after having said this. You see, you can draw, so in 2 dimensions, it's still the blackboard, okay? So here you have CT, and here you have one direction. The others are sort of, they go for the ride because I fixed them. And you can, let's take C equal to 1, okay? So that in unity with C is equal to 1, you can draw 2 lines like this. And we learn that the distances along these lines are 0, right? Because they are distances in this direction. Okay, and so you see you have, so on this line, distances are equal to 0. So ds squared, the distance measured there, is effectively equal to 0. Inside this triangle that is really, if I bring back x and y, they are cones, right, like this. You have ds squared is greater than 0. And in between this and this, so here, ds squared is less than 0. Okay? So space-time, Minkowski space-time, is effectively divided in 3 regions. One in which the interval are ds squared is greater than 0. So this is it's called a now I'm stuck again. So ds squared, yeah. So this is, so if you are here and you start moving, you see you have that, you can only, so you can only move inside this cone or this line, because to move here you must move at the speed of light, right? Because c equal to 1. So if you start moving at the speed of light, you move along this line. So this line is called the light cone, right? That defines, and it separates effectively regions that are connected through intervals that are traveled by an observer. So if you start moving, you move slower than the speed of light, so you move inside here and you reach maybe this point in space-time. Points that are, so if you are here, you can never communicate, right? Because the faster that you can communicate is the speed of light. So you can reach, as time goes by, you reach all these points, but you never reach one that is here. You reach the observer here when this goes up, and it reaches here, maybe, if you communicate with light. So this is a completely disconnected section of space-time. And so this is your future, if you start out here. And clearly, this other cone is your past. And everything that is here is the present. But you see, you cannot communicate with everywhere in space because of the fact that you can only communicate using light, and light moves with a final speed that is equal to c, that is equal to 1 here. Okay? You see, this is the equation, is exactly the same, the front, the equation of the wave, right? So this is the light propagating, this is the future, and that is the path. So what else? Have you seen that before, or is that the first time you see this? So this is a Minkowski space time. So as we computed before, I mean, the distance in Minkowski space between two light points, I mean, points on the light cone is just 0. These is the characteristic, okay? So in fact, you see, there is no way that you can communicate. So this is the original, you know, if you have a fixed clock with you, these are different times. And you see, I mean, at the same time, two observers that are here and here, they cannot know of each other because they are the same time, but there is no way that they can communicate, because if this one is communicating with that one, is sending out a light signal, and it will reach this guy only here, right, as it moves in time. So this is useful because you have to, when you discuss physical problems, you should discuss them in this space, okay? Like before, you discuss them in space by using the Cartesian coordinate. Here you use this Cartesian coordinate, except that you have this Minkowski matrix in which you have this minus sign that, of course, changes everything in this form, okay? So what happened when you take two observers? You take two observers. So the first things you notice is that because of these Lorentz transformations, as I said, time is not the same for observers moving at different speed with respect to each other. In fact, if you look at the formula of the boost, you see that if you are looking at the clock in another, if somebody with a wristwatch is walking past you with a certain speed, you will observe that the two times click at different rates, right? So how that this, and it's completely reciprocal. That is, if I'm looking at your clock and your clock is speeding up with respect to mine, or and you look at mine, you will see the same effect, right? You see that mine is actually running faster than yours. Or, as they said, they usually talk about this paradox of the twins, I guess. The twins. So you take two twins, right? How does it work? In fact, you have to draw this space-time diagram, sort of. Okay, so how does it work? Do you remember? You have so you have two twins, and one remains on the Earth, so it just stay in the same place. So this is time. C is equal to 1, and the other guy is on a spaceship, moving very fast. We will see how fast in a second. So I guess he goes very far away to some other star. And then he comes back, right? Now, because, so how does it look like? That you have this fact that the time is running at different rates in the two frame of references. So usually you say this guy is getting older. I mean, he goes very far away, so it takes, I don't know, 100 years. Okay, but because of the Lorentz transformation, really times for the guy that is boosted, that is moving fast, it goes much slower. So the clock here is clicking slower than the clock on the Earth. So this guy, maybe it takes like 20 years to go from here to here. Meanwhile, on the Earth, 100 years have elapsed, right? So this guy, the two twins, when they meet again, the guy who stay here is 100 years old, the other one's 20 years old. And the paradox is that, what is the paradox? No, what is the problem with this? Yes, but what is the problem here? Right. I mean, as I said, I mean, we have these things that, okay, times is running slower here, but the same, you know, you can think of the spaceship remaining here and the planet moving, right? It should be completely symmetric. In that case, it's the guy on the spaceship that is seeing the other guy moving at the speed very close to the speed of light. So it's the other guy who should remain young, right? This is the paradox. So how does it work? Do you want to think about it and we discuss it on Monday, or you want to give a try? No, I rather not bring. Let's assume that this guy jumps here. It's a very delta function, Dirac delta function things. I mean, you don't want to discuss gravity. This is Einstein's answer, but so think about it. So this is the homework. And of course, you have the equivalent problem. It's not trivial. I mean, the answer. I mean, it's not completely trivial. Okay, but so maybe you want to start with a similar problem in space, right? Because again, because of the Lorentz transformations, right? You also have these things that if you start measuring something that is moving with respect to you, like time, you will see that shorter, right? So also that is kind of strange. And so, for instance, say you are a pole vaulting, you know, this long, or this one, and you start running. And let's assume that you run. So this is the other sort of problem. So you are running, and you are holding something that is, say, 10 meters long. At a certain point, there is a barn. Okay, that is, I don't know, 8 meters long with 2 doors. So the observer that is sitting here on the barn, so provided that you run fast enough, I mean, with the speed close to the speed of light sufficiently, we'll see this shorter, right? And assume that the speed is short enough to be 8 meters. So when you are inside, for an instant, the guy there closes both doors. That seems to be okay, right? Because, this is 10 meters, but because it's moving, it's shorter. You close the doors, and then it's open, and you pass through. Now, you understand that from your point of view, this is very strange because you are running. Now, for you, this is 10 meters because there is no contraction. But the barn is even shorter because, I don't know, it's 6 meters. So the guy closed the doors, and, you know, how can that be? You see, it always has to do with the fact that the physics should be the same, right? I mean, either these things get through or not, or it doesn't. But it looks like it cannot. So, okay, I want you to think also of this one. So this is homework 2. So this is the twins. So this is the twin paradox, or twins paradox. But it's not a paradox. I mean, paradox means that there is a real contradiction. And this is the ladder and barn, or the pole vaulting, or whatever you want to call it. Yes?
The two plates are in motion. Maybe one.
The two?
The two plates, one should be because there are two watch, I don't know, two horloges.
Two clocks.
Yeah, two clocks. So one is in motion, I think. Yes, in moving. One is moving.
Yeah.
So one should be.
No, but it's not. I mean, they from the point of view special relativity, they are both moving. If you want, I mean,
Yeah, but
because
the two horloges are in moving. So how you can know?
no, but I mean,
It's at a soft time.
no, I don't understand. I mean, one for the guy on the Earth, the clock on the ship, on the spaceship is moving, but for the guy, I mean, on the spaceship, he may say it's the Earth that is moving, right? I mean, it's still true that physics is the same in all frames of references moving with constant speed. So it's all. That's why it's called relativity. I mean, because okay, what you tell me.
In French or in
Yeah.
English, I don't know exactly, but in French, I can say les horloges en mouvement retardent les horloges fixes.
No, the point is exactly this, that the guy here sees a retardation in time, but the same should be true for the other guy. But clearly it's not, because it's like here. This guy sees this shrinking, but this guy is seeing the barn shrinking. But at the end of the day, he should, I mean, the result is the same, that this guy is older than this. This is an experimental fact. I mean, if you have muons coming into the atmospheres, right, you know that they live longer than, the muon decays, I don't know, in a fraction of a second, but we find muons much at a lower altitude than they should have decay. But because they move very fast, they decay much, for us, slower than for them. So this is a fact. We have the twins. And this too is a fact, even though I mean, we don't have people running that fast. So I just want you to think. I mean, people, they thought immediately. I mean, Einstein explained that it's a gravitational fact because here you have a tremendous acceleration. So this is okay. It's a possible solution. But there is also a solution that in which, say, the guy here simply throw the clock to another guy coming in the other direction. And this happening in a delta, okay? So let's assume this, just for the fun. It can be explained. But okay, so we will discuss this on Monday. We play around with this relativity stuff. Do you have questions? Okay, so that's. So these Lorentz transformations, they came about, remember, just maybe this is the main point to remember. So we require the wave equations to be preserved, right? So that means that first, we want the physics, exactly as in Galilean physics, the same, be the invariant in form, all our equations, independently of whether you are moving with a constant speed with respect to one observer and the other. But the other thing, because we want the wave equations to remain invariant, we have that the velocity of propagation of that wave, that is light, must be the same in all of these frame of references. So it's a little bit, you know, these two requirements that produce the Lorentz transformations are a little bit. I think this second one is it's harder to digest, right? Because we have the idea that if you are moving, you know, the car moves, then you turn on the headlights. So what is the speed of the light from the headlights? Should be c plus the speed of the car, but that's not the case, right? Because it's a wave, as I said before. I mean, if I'm talking and I'm moving, the speed of sound is the speed of sound in that medium. It does not depend on the motion of the radiating source. So from this point of view, it's obvious that the speed of light is the same in all frames, right? That's the beauty of Einstein's idea. On the other, it goes against our general idea that instead light is not, I mean, it may be a particle or something in which you sum the speeds. Okay, so that's what has to be digested. And of course, the problem, as I said maybe earlier, is that this idea that the speed of a wave does not depend on the velocity of the source. It's physically clear if you have a medium, right? Because you excite the medium, and that's the wave. But here we don't have this medium because we only have these two vectors in empty space, E and B, and therefore it's a bit harder to understand, okay? But that's what it is. I mean, this has been verified many times that you have to use Lorentz transformations to go from one frame to the other. So there is little doubt that this is correct. I think it's so for our discussion on Monday, it's also useful to write the. You see, you can write in a nice form these Lorentz transformations if you introduce a sort of. So let's take again the Lorentz boost, but let's introduce an angle. So I introduce the tang. This is the ratio of the sinh over the hyperbolic stuff. So I call beta this V over C. I identify with this angle. Okay. So you see that because of the property of this, so maybe let me. It's easier to call the tangent. So you remember that the hyperbolic tangent, right, is like the sinh divided by the cosinh, right? And the cosinh square minus the sinh square is equal to 1. Now you understand why, I mean, why I did not use the tangent. Because of this freaky minus sign in the time component, I need something that looks like this minus that rather than plus. So you have to use hyperbolic function. Now you see that if you identify the tangent, the hyperbolic tangent with beta, then the sinh is V over C divided by 1 minus V square C square, and the cosinh is 1 minus V square C square, right, by using this decomposition. So if you remember the boost I wrote before, now I can write the boost, the generic boost for the T component that by now I can call X naught, is going to be, remember, it was like this, so it was the hyperbolic cosine of this angle theta that is related to the boost parameter beta, the theta of X naught minus the sinh theta of X1. I'm still boosting only in one direction, okay? so this is time, and the x direction, you see, is minus the sinh of theta x naught plus the cosine theta of x1. And the others are the same, right? Y and z, so. Do you see that? Or yes, no? I mean, no. So you see, if I define this angle in such a way that the hyperbolical tangent is equal to beta, then if you use this property, right, you see that so here I forgot, that the hyperbolical sine must be V over C divided by this, and the cosine is equal to this, right? This is just mathematics. But you see, these two are the factor that were in the boost that I wrote 1 hour ago, right? You see, because well, that was the boost. So I can take this. This was the boost. If you put this was this factor gamma, right? And then that was the other combination. So you see, you can write the boost by using this hyperbolic transformation in a way. But that's kind of nice because you see, this is like a rotation. So now a Lorentz transformation is a rotation in space-time. But what kind of rotation? It's not the usual rotation because you see, I don't have the sine and the cosine. I have the hyperbolic sine and hyperbolic cosine. So it's a little bit different. That is, if you start with your first system with coordinate x1 and x0, and you do a boost, it is a rotation, but it's not the rotation that we are used to in which this rotates like this. It's a rotation in which they come closer. So this goes to a new set of coordinate system by this angle theta. This is it's a very nice representation of what is going on. In fact, it may help you to discuss those two, the twins and the ladder and barn paradoxes, if you map the problem in these coordinates. Because in these coordinates, you see just a rotation. So you start out, you see, and then when you measure things, here in this frame, you measure things by drawing this line, right? 1, 2, 3, and 1, 2, 3. But here you should do the same, but you see the lines are like this. So the same object that was long like this here becomes something like this in the other frame. So by using this rotation, well, rotations like this, you can, for instance, this fact that two events are, let's do this. I start with this x1 and x0, right? And then I have this boost, x1 prime and x0 prime. Huh? So you see that if you have two, for instance, now you go to a line here, and you take two events, A and B. Right? You see, this line ends exactly at the same point in time for this set of coordinates. For this observer, A and B are simultaneous. You see, these two events happen exactly at the same instant because how you draw a simultaneity line? You draw parallel to the x direction, right? So A, B are exactly at the same time x0 prime. But you see that if you draw the simultaneity line in the other space, then you have to draw lines parallel to the x1 coordinate, so they are like this. So you see they happen at 2c delta t, at two different instants in time. So this is very useful because it visualizes this fact that two events that they happen exactly at the same time in this frame, moving with a certain speed with respect to the other, they will look separate by the interval of time. So not simultaneous at all in the other frame of reference. And this is the most important information, that things that happen at the same time in a frame of references, they happen at different time in another one. So there is not a single time in the whole universe for all observers. What is time depends on the frame of reference in which you happen to be living. Okay, so that's a useful thing, I think, to think in this boost as rotations, but they are rotations in which you don't rotate the axis like this, but you pull them close. So they are rotations defined by the hyperbolic functions rather than the trigonometric functions. So for instance, now you can start thinking about the barn and ladder, because you see, when the two doors are closed, right, the guy there say, when the ladder is inside, I close the two doors. So he thinks he's closing the two doors at the same time. But this same time is not the same time for the guy who's running. So there the explanation has to do with the fact that actually for the guy running, first one door is closed and then the other one is closed. Not at the same time. That allows for the much longer pole to get through. So
What really happens?
So this is what really happens. We live in a Minkowski space. We don't live in a Cartesian. That's an experimental fact. I mean, this is what really is happening. That if you check clocks and you are moving, our clocks do not move at the same time. So what is simultaneous for you is not for me. I mean, that's how the work. I mean, the world is like this. It's like it's quantum and relativistic. It's weird, but that's the way it is. You seem skeptical. No, I mean, clearly your everyday experience it goes against that, but just because you move so slowly. If if we were all, there is a nice book by Gamov. Maybe you have read that. How is that? Mr. Tompkins or something. Where you see, to understand relativity, you really should think that c is not. What is it? 1/10⁹ centimeter per second, maybe. Okay, but think that it's like 10 kilometers per hour. Assume that the speed of light is the speed of a bicycle. Now all these effects will be part of our everyday life. So as I walk this direction, you see me, much thinner in these directions, right? Because I have a Lorentz contraction. Right? The same, and our clocks are completely, because I move a little bit, my clock is completely different from yours. We would never agree on when to have class, unless we all move it. So that's the way it is for particles, right? They move very close to the speed of light, and as I said, the muons, they decay much later than they should because they move with respect to us. They live in a frame moving with the speed very close to the speed of light. So these are real effects. And Of course, Lorentz thought that the Lorentz contraction was a physical effect in the same frames, right? I mean, Lorentz wrote the Lorentz transformation before Einstein. But he thought that this fact of that if you see something moving past you, you will see it shorter than the guy. He thought that that was a physical effect, that if I run and I see as well as you see this I don't know how it's called, this pointer shorter. Because the idea was that to solve this question with the boost, really the atoms were getting squeezed because they were moving very fast. So they were like with your hair like this. So they really thought that if you ran, but this is not what happens, right? This was Einstein's contribution. The guy running with this pole toward the barn sees the pole exactly 10 meters. I mean, that's what it is. It's you who sits on top of the barn that measure my pole running that you see it shorter, and vice versa. So it's a problem of you measuring something in another frame. So there is no, how to say, the Lorentz contraction as explained to us by Einstein is not that the atoms get anything weird or stuck together closer. It's just you that are measuring something in a frame that is moving with respect to you that see that shorter. The same with time, okay? So maybe that's it's not a physical effect on the things. It is a physical effect, but due to the fact that you are moving with respect to me. But that then leads to those paradoxes because it's completely symmetric. Then you have to explain things like but it's not a big deal. I mean, it's just a question of simultaneity or not. In fact, on the Wikipedia, I found two quite nice articles on the twin paradox, and so you are welcome to inspire yourself by reading them. And also on this ladder paradox is called there. So the last thing, I want to use this to show this fact that is maybe a paradox too, that because if we are moving with respect to each other with certain v, I see your stuff shorter, but you see my stuff shorter. So how that can be? This is a very common objection to relativity. I mean, it makes no sense because I see your ladder shorter, but vice versa, you see if I'm running the same shorter. So how is that possible? Well, this is actually has to do with these diagrams. So let's look at this boost from the two frames and use the geometry of Minkowski to explain this symmetry of the two, and then we stop. So as I said, so it seems impossible, right? Because if I draw, so this is x1 and this is time. And then I have the other frame that is moving in which time is this. Let's call it like this. And so so say I have something, a length L here, right? This is space, so a length L goes from here to here, right? At time t prime equal to 0. And the contraction, Lorentz contraction, is the fact that when I take this length, looks only like this, right? This is Lorentz contraction. That the length measured in this frame, you see, looks shorter when measured in the other frame. So how is it possible that the same should be true? If I measure this, I go back here, it should be shorter, but it's not, right? It's longer. But is it? Actually, it's not, because the problem here is that you have to measure these distances, right? So you need something invariant to report the unit of length. So I don't know if I can do this because it requires some drawing. So let's see. I start out. So this is x, and this is time, right? This is x prime. So I start with the length x equal to 1 here. Okay. The origin, point A, is x equal to 1. Okay. Now you see the problem is that I have to, so this is the unit length. I have to report this unit length in the new boosted frame. How should I do that? To do that, I need something that is invariant, and the only thing that is invariant under this transformation is by definition the x squared minus c squared t squared equal to, in this case, 1. So this is a hyperbole in this space, right? And this is invariant under the transformation. So this goes like this. This is half of the hyperbole. Okay? So you see this point A, that is 1, goes to this point, I call it, I don't know, A prime, that is x prime equal to 1. This is the one in this new set of coordinates. Okay? So you see that when I report this length 1 here, I go up straight. So I go to this point. Okay? But you see, this is not 1. It's less than 1. Because 1 is not what you would go straight up. You have to transform this 1 in an invariant manner. So you go up, say, through this hyperbole. Okay? So you see, then this one is shorter. Because 1 was this. When I measure 1 in this unit, this is shorter, even though it looks like it was. And the same if I go back. Right? Because if I go back, this A prime, I have to report this parallel to the other axis, right? So this goes back here. You see, this goes up this way, this goes down this way, because when you report lengths at fixed time, you have to move parallel to the time. So you see, this too goes in a point I prime that is shorter than the original. So both are shorter. So it's perfectly okay. And to understand it, you have to use this geometry. You should not use your mind, because we know that it does not work, because our mind developed through evolution in a space that was not Minkowski. So you cannot pretend to understand. But you see, it works perfectly fine. So you see, it's completely the same. This is shorter than this, but also this is shorter than that, because the invariance of the unit has to be reported through the hyperbole. So that too helps with the ladder paradox. Okay, well, now it's so we keep on. So on Friday we will move on with the space-time and write the Maxwell equations in this space. Yes.
Do we have a space in which we do not dissipate like length contraction, time dilation?
Well, just Cartesian.
No, we have Cartesian.
Yeah, I mean, if you have
No,
t.
4D and
Yeah, but.
we have space and we have time. But
Yeah, but if time is not transformed in the boost, then you don't have these effects. These effects come in because I require this invariance. Then I get this mixing between space and time. So I have the Lorentz boost. If I don't have the Lorentz boost, t is equal to t prime. So I just have rotations, and for rotations I don't have this.
Okay. I mean, if we have like Lorentz transformation, then can we have space in which?
No, because the space that is invariant under Lorentz transformation is Minkowski, and Minkowski is made this way. Then
Why we need to introduce the matrix tensor? I mean, why would we write like x is x1, x2, x3, and then ICTP.
No, I don't write I. I wrote minus. I don't like this I.
Okay, I don't know.
No, don't write I. It's because then you have rotations, but then you see.
We can, when we transfer, we just put the minus sign and then we do.
Yeah, but you have one component that is imaginary, so I think you pay too high a price. Just stick with the real coordinates and the Minkowski space. I know that the old way was to put an I, then this tangent hyperbolic becomes a tangent, then these are rotation. But then it's even more complicated to understand all this stuff. No, believe me, but follow me. Don't. We live in this Minkowski space, and actually the space is even more complicated than Minkowski, as you know, because this is a flat space, but you know that if you want to bring in gravity, this Minkowski space becomes curved, so it's even more complicated.